Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 10, Projective Transformations of Two-Dimensional Forms. Section 97, Double Pairs of a Correlation. We inquire now regarding the existence of double pairs of a correlation in a plane. By a double pair is meant a point X and a line U such that the correlation transforms X into U and also transforms U into X. In symbols, if gamma is the correlation, such that gamma of X equals U and gamma of U equals X. We have already seen, Theorem 3, that if the vertices and opposite sides of a triangle are double pairs of a correlation, the correlation is a polarity. We may note first that the problem of finding the double pairs of a correlation is in one form equivalent to finding the double elements of a certain collineation. In fact, a double pair XU is such that gamma of X equals U and gamma squared of X equals gamma of U equals X, so that the point of a double pair of a correlation gamma is a double point of the collineation gamma squared. Similarly, it may be seen that the lines of the double pairs are the double lines of the collineation gamma squared. It follows also from these considerations that gamma is a polarity if gamma squared is the identical collineation. Analytically, the problem of determining the double pairs of a correlation leads to the question, for what values of x1, x2, x3 are the coordinates a11x1 plus a21x2 plus a31x3, a12x1 plus a22x2 plus a32x3, a13x1 plus a23x2 plus a33x3, of a line to which it corresponds proportional to the coordinates a11x1 plus a12x2 plus a13x3, a21x1 plus a22x2 plus a23x3, a31x1 plus a32x2 plus a33x3, of the line which corresponds to it in the given correlation. If ρ is the unknown factor of proportionality, this condition is expressed by the equations 1. The quantity a11 minus ρ a11 times x1 plus the quantity a12 minus ρ a21 times x2 plus the quantity a13 minus ρ a31 times x3 equals 0. The quantity a21 minus ρ a12 times x1 plus the quantity a22 minus ρ a22 times x2 plus the quantity a23 minus ρ a32 times x3 equals 0. The quantity a31 minus ρ a13 times x1 plus the quantity a32 minus ρ a23 times x2 plus the quantity a33 minus ρ a33 times x3 equals 0, which must be satisfied by the coordinates x1, x2, x3 of any point of a double pair. The remainder of the treatment of this problem is similar to the corresponding part of the problem of determining the double elements of a collineation, section 96. The factor of proportionality ρ is determined by the equation 2. The determinant by column a11 minus ρ a11, a21 minus ρ a12, a31 minus ρ a13. a12 minus ρ a21, a22 minus ρ a22, a32 minus ρ a23, a13 minus ρ a31, a23 minus ρ a32, a33 minus ρ a33 equals 0, which is of the third degree and has, under proposition K2, 3 roots, of which one is 1, and of which the other 2 may be proper or improper. Every root of this equation, when substituted for ρ in equation 1, renders these equations consistent. The coordinates x1, x2, x3 are then determined by solving 2 of these. If the reciprocity in question is a polarity, equations 1 must be satisfied identically, i.e., for every set of values x1, x2, x3. This would imply that all the relations a sub ij minus rho a sub ji equals 0 for ij equal 1, 2, 3 are satisfied. Let us suppose first that at least one of the diagonal elements of the matrix of the coefficients a sub ij be different from 0. If this be a11, the relation a11 minus rho a11 equals 0 gives at once rho equals 1, and this value leads at once to the further relations a sub ij equals a sub ji for ij equal 1, 2, 3. The matrix in question must be symmetrical. If, on the other hand, we have a11 equals a22 equals a33 equals 0, there must be some coefficient a sub ij different from 0. Suppose, for example, a12 not equal to 0. Then the relation a12 minus k a21 equals 0 shows that neither k nor a21 can be 0. The substitution of 1 in the other of the relations a12 equals ka 21 and a21 equals ka 12 then gives k squared equals 1, or k is equal to plus or minus 1. The value k equal 1 again leads to the condition that the matrix of the coefficients be symmetrical. The value k equals negative 1 gives a sub ii equals 0 and a sub ij equals negative a sub ji, which would render the matrix skew symmetrical. The determinant of the transformation would on this supposition vanish, since every skew symmetrical determinant of odd order vanishes, which is contrary to the hypothesis. The value k equals negative 1 is therefore impossible. We have thus been led to the following theorem. Theorem 7. The necessary and sufficient condition that a reciprocity in a plane be a polarity is that the matrix of its coefficients be symmetrical. If the coordinate system is chosen so that the point which corresponds to rho equals 1 in equation 2 is 1, 0, 0, it is clear that we must have a21 equals a12 and a31 equals a13. If the line corresponding doubly to 1, 0, 0 does not pass through it, the coordinates 1, 0, 0 may be assigned to this line. The equations of the correlation thus assume the form, equations 3. Rho u1 prime equals a11x1. Rho u2 prime equals a22x2 plus a23x3. Rho u3 prime equals a32x2 plus a33x3. And equation 2 reduces to equation 4. a11 times the quantity, 1 minus rho, times the determinant, a22 minus rho a22, a32 minus rho a23, a23 minus rho a32, a33 minus rho a33 equals 0. The roots other than 1 of this equation clearly correspond to points on 1, 0, 0. Choosing one of these points, proposition K2, as 0, 0, 1, we have either a23 equals a32, which would lead to a polarity, or a33 equals 0. In the latter case, it is evident that equation 4 has a double root if a32 equals negative a23, but that otherwise it has two distinct roots. Therefore, a correlation in which the point 1, 0, 0 and the line 1, 0, 0 correspond doubly and which is not a polarity may be reduced to one of the three forms. Form 1. Rho u1 prime equals ax1. Rho u2 prime equals bx2 plus cx3. Rho u3 prime equals x2, where 0 is not equal to c is not equal to plus or minus 1, and a not equal to 0. Form 2. Rho u1 prime equals ax1. Rho u2 prime equals bx2 minus x3. Rho u3 prime equals x2, where a is not equal to 0 and b not equal to 0. Form 4 u1 prime equals ax1, rho u2 prime equals negative x3, rho u3 prime equals x2, where a is not equal to 0. The squares of these correlations are collineations of types 1, 2, 4, respectively. If the line, doubly corresponding to 1, 0, 0, does not pass through it, the coordinates 0, 1, 0 may be assigned to this line, and the equation of the correlation becomes rho u1 prime equals x2, rho u2 prime equals x1 plus a22 x2 plus a23 x3. Rho u3 prime equals a32 x2 plus a33 x3, where a33 is not equal to 0 and a23 is not equal to a32. Equation 2 at the same time reduces to a33 times the quantity 1 minus rho cubed equals 0, and the square of the correlation is always of type 3. There are thus 5 types of correlations: the polarity and those whose squares are collineations of types 1, 2, 3, 4. Exercises. 1. The points which lie upon the lines to which they correspond in a correlation form a conic section c squared, and the lines which lie upon the points to which they correspond are tangents to the conic k squared. How are c squared and k squared related? In each of the 5 types of correlations, to one another and to the doubly corresponding elements. 2. A line A does not lie upon the point A prime to which it corresponds in a correlation. There is a projectivity between the points of A and the points in which their corresponding lines meet A. In the case of a polarity, this projectivity is always an involution. In any other correlation, the lines upon which this projectivity is involutoric all pass through a unique fixed point O. The line O, having the dual property, corresponds doubly to O. The double points of the involutions on the lines through O are on the conic c squared, and the double lines of the involutions on the points of k squared are tangent to k squared. O and O are polar with respect to c squared and k squared. If a correlation determines involutions on 3 non-concurrent lines, it is a polarity. 3. The lines of k squared through a point P of c squared are the line which is transformed into P, and the line into which P is transformed by the given correlation. 4. In a polarity, c squared and k squared are the same conic. 5. A necessary and sufficient condition that a collineation be the product of 2 reflections is the existence of a correlation which is left invariant by the collineation. Footnote: this is a special case of the theorem of Dunham-Jackson, Transactions of the American Mathematical Society, Volume 10, 1909, page 479.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.